So yeah, there are many things that we can represent with a single bit. But honestly, there are many more complex things in our life that need more than just a yes-no answer to be understood, talked about, thought about, communicated, and so on. So to be able to represent something more complex than simple yes-no questions, what we can do is bundle up many bits together and have them exist as a single package of multiple bits. Then comes the question though, how many bits should we use for a single package? Well, let's start with checking out what if we take 2 bits. So here's an adapted circuit diagram, this time carrying 2 different bits that we can control. Remember, as we said before, since a bit is an individual wire or line of electrical connection, we can go ahead and circle the 2 different bits here. So if you look at where electricity would not be flowing from that switch here being open, you would see that it's the entirety of this wire here in the circuit through which no electricity would flow. Now the same thing separately looking at this switch up here. If this switch was open or closed, that would determine electricity to be on or off within this portion of the circuit, or this specific wire here that I'm going to circle. Now that's because that junction point over here is pretty much what separates these 2 wires from being controlled or affected by each other. So in effect, this is the first bit here. That's bit number 1. And this is the second bit. Bit number 2. And so that's for 2 bits. Now if you wanted to add another bit into this circuit, all you would need to do is, for example, add another wire portion here with the switch coming out, and then with the light bulb, and then back in like that, and you've added a 3rd bit to your circuit. Finally, once again, we can take out the light bulbs from the circuit and it would be equivalent as far as we're concerned with bits. But again, we're using the light bulbs to help provide us an indication as to the electrical state of each of those portions of wires. Now, if we look at the bundle just as a whole and just ask how many are on or off at that time, there are only really 3 possibilities that we have. Either both bits are on, either both bits are off, or one bit is on and the other is off, where the combination of off on and on off mean the same thing. If we say now that order matters, then we have 4 possibilities now, both on, both off, then the first one on and the second one off, and the first one off and the second one on. If we think about it, if we want to use these bits to implement a certain code, then we would definitely care about the order of the bits, because what this will do is will give us the maximum number of possible states for this given set of bits. So if we maintain that the order of the bits matter, a bundle of 2 bits can be in 4 different states, as we see here on the left: 2 on, first one on, second one on, and both off. So a code that uses 2 bits will be able to differentiate between 4 different states. And the more states we have for a particular bundle, the more complicated code we can make. And we'll see what I mean by this very quickly. So that was for 2 bits. But what about bundles of 3, 4, 5, even more bits? Well, the thing we really care about here when looking at a package of bits, what we really want to know is how many states can this package of bits be in, so that we can implement a code assigning each of those different states to a particular meaning. So what we do want to know is how many possible states exist for a package of X number of bits. Well, if we look at 2 bits here, we see there are 4 possibilities. Basically, to make that calculation, all you need to do is count the number of bits in that package and use that as the power of 2. You start with 2 because your first bulb, or your first bit, can be in one of 2 states. And then the second bit can also be in one of 2 states. So now you have 2 bits that could be in either 1 or 2 states. So we know that 2, the number of states per bit, is a core number. And then the number of bits is the power. So if we extend this to more bits per package, we see that a package of 3 bits can be in 8 possible states. And that's because the first bit could be either on or off, the second bit could be either on or off, and the third bit could be on or off. Those are combinations of two possible states 3 times over. And so the formula is basically 2, which is the number of possible states, to the power of 3, which is the number of bits that can be in those two possible states. So for a package of 4 bits, we actually have a name for this called a nibble. The total number of possible states those 4 bits in total could be in is 16, as 2 to the power of 4 is 16. For a package of 8 bits, which we also call a byte, the total possible states is 256. That's because there are 8 different bits that can be in either an on or off state. And so there are 8 combinations of 2 possible states. And so we arrive at 256 possible states for that byte. So that last bundle we talked about has a specific name, and that's a byte. A byte is simply a bundle of 8 ordered bits packaged together. And so you can think of it as just 8 wires next to each other, where each wire could have electricity flowing through it or not. And because a single byte can be in 256 total different states, if we decide what each state means, then it can represent 256 different states of information. And we can create a code with 256 states of a particular byte and assign meaning to each of those 256 unique states. And the computer science community felt this was sufficient enough to represent most of the world's information. So as a result, the byte became the standard unit of information in computer science. Just quickly before we move on to the next part, we do need a better way to represent bits than light bulbs. So instead, we're going to be using numbers 1 for on and 0 for off. You've almost definitely seen this 1-0 notation before. This 1-0 system, as you may already know, is called binary. The binary system is what we use to represent wires being on and off. That is the system we use to represent the states of information that a computer can read, update, edit, and delete. There's also the binary number system, which is more of a numerical system of counting, which doesn't have anything to do with the actual electricity that's running inside wires in a computer. Once again, don't worry too much about this. Eventually, we'll understand the difference between machine binary and numerical binary, as well as what this means as far as you're concerned when it comes to programming. So now it's time for us to make another code, and this time for bytes. So with a byte, we now have 256 different states to make a code from. And that means 256 different pieces of information can be created out of a single byte. So to make a code that would be applicable to the real world, now would be a good time to ask yourself, what kind of units of information do you work with in your life? The first thing that could come to mind is written language, right? I mean, we use written and spoken language to achieve all the communication that happens on this planet. So the first thing we need to enable the use of the English language are letters, right? We need letters to combine them in different ways to create words so that we can have a vocabulary, so that we can express ourselves in ways that other people can understand. So we have 26 letters in the alphabet. If we take them in lowercase and in uppercase, then we need 52 places in this code reserved for letters specifically. And we also have digits in our language, right? We need to represent quantities in some way, and we need quantities to be able to measure certain things as compared to others. You know, like your self-worth as an individual based on the number of likes you get on an Instagram post. Because we all know that is a top indicator for that. So we're going to reserve 10 spots for our digits. Then we have the rest of our code space to fill in with whatever we want. Mainly now what we have left are pretty much our punctuation and special letters like commas, colons, and quotations are used to separate main key points in a sentence, as well as exclamation marks for punctuation, as well as spaces to actually separate the words that we're talking about. So all of these symbols have a special name, and that is a character. A letter, number, or any symbol used in written language is called a character. So when it comes to building this particular code for our bytes, we say that a particular state of the byte represents a particular character used in written language. So we have the space to fit all our characters in the 256 possible states of bytes. So how do we actually make the code? So like I said before, each character will be represented by a byte that's in a specific combination of ones and zeros, or in a specific state. So to actually make the code, all we need is for someone, just one person, anybody, to just sit down, list all 256 combinations of bits that make up the byte, or that make up the byte state, and next to each state of the byte, put the character that they want to be represented by that byte. So to go back to this table quickly here on the right, we basically need somebody to make an equivalent table for this, but instead of it saying bit state, it would say byte state, and instead of being on and off, there would be many more rows here, 256 rows, for each of the different combinations of on, off, on, off, on, off, for 8 of the bits in that particular byte. The representation is a specific character, and that character can have a certain meaning. It's up to you. So is there an equivalent? Has somebody already done this? Of course. Historically, when computer science was just taking off and the concept of bits and bytes were coming into play, we were able to harness and manage bits, and we were able to bundle them into bytes and actually compute them in meaningful ways. So originally, each company and organization in the computer science space was making up their own codes to represent English language. As you can imagine, all the different companies ended up realizing that they were trying to do the same thing. And so one day they all just decided to sit down and agree on a specific code that everybody should use. I have no knowledge or idea of what these meetings involved, how long they were, how excruciatingly painful or boring they could have been, how many people left these meetings angry, probably a lot. But eventually they did reach an agreement, and so was born the American Standard Code for Information Interchange. So here's a snapshot of basically the entire ASCII code. All of the different states of the byte, which is under the binary column, and the ASCII equivalent, which is under the ASCII column. So like I said before, each byte code is unique, and one state of the byte corresponds to a single character. So for example, if we look at the ASCII code A here, circled in red, uppercase A, we see that the binary or the byte state is 0, 1, 0, 0, 0, 0, 0, 1. Now, if you look anywhere else in that list, you will not find the same binary sequence of 0, 1, 0, 0, 0, 0, 0, 1. It won't be anywhere else in this code because you can only use one byte state to represent one particular character. Now, another thing that you can note is that there are only 128 characters being used here in this ASCII code. So technically, we could even apply this ASCII code to a 7-bit package. If you notice, the first number of all of the bytes in this code is 0. Now, I'm quite sure that when ASCII was originally written, it did apply to 7-bit packages. However, now ASCII has been incorporated into another code called UTF, which uses 8-bit packages. Once again, don't worry about what I just said there. Eventually we'll understand what we mean by UTF. So think of this now. If I wanted to write the word hello in the form of the wires and switches like I had in my diagram, and applying the ASCII code to give meaning to each of the bytes, how would I do it? Well, it's pretty simple, right? I would start by taking the first character of hello, which is H, or uppercase H, let's say, and I would set my first bundle of wires so that they represent the binary number 0100 1000. And so I would just close the second and the fifth switch in my bundle of wires, and I would be representing the letter H with bytes as applied under the ASCII code. And then I would just do that for the rest of the letters in the word hello with other bytes, other bundles of wires, and put them together. I mean, looking at it, I would not see anything meaningful because it's just a bunch of wires. But then after applying the ASCII code to all of them, I'd be able to spell out the word hello. So what you might be thinking now, right, is if a computer needs to be able to store multiple words and sentences, it will need multiple groups of 8 wires or multiple bytes where each wire can have electricity running through it or not and can be set to be on or off. So to close off that topic, the last thing I do want to say is that ASCII is not the only code used in computers to give meaning to bytes. For example, I don't know if you noticed from this picture, but if you look at the binary column, on the left of it there's also a decimal column. This decimal number is the quantity that is equivalent in the decimal system to the binary number next to it in the binary system. The decimal system is a numbering system you and I are most familiar with. It's the one that we've grown up with, where we have 9 digits which we can use to represent all the numbers that we can imagine. Now starting from 0, when you count up to 9, which is the 9th number in our system, we've run out of digits, so we start again at the 10th number by writing 1 0 and start again from there. In binary, we only have 2 digits, 1 and 0. That means when counting up from 0, you add another number once you've run out of digits in the first row, which is at number 1. So to represent number 2, we represent it as really 1 0. Now in our context of bytes, decimal numbers really have no place nor really any meaning when it comes to wires with electricity. I mean, even if you just look at the ASCII code for the digits 0 to 9, they don't correspond to any kind of number at all in the decimal system. So that should really tell you something about how to think of these values and how to think of what bytes actually are and the importance of using a code. Now you may think that you need to become somewhat good at understanding the conversion between decimal and binary, even hexadecimal, which is a 16-base number system. As you can see from the table there, just pause the video to have a look at what the hexadecimal equivalents are, if you want to. Really, if you want to be a good programmer and want to be someone who feels complete and well educated about the subject, you're better off understanding that binary in and of itself, first and foremost, relates to representing the state of the wires in a particular byte as being on or off with 1 or 0. Then in secondary, binary also refers to a numbering system, just like the decimal system. But that is something that is in and of its own different from actually representing the states of the wires. Now, interestingly, since the binary numbering system is already in 1s and 0s, it does indeed make sense for computers to do certain mathematical operations in binary because they already have the number equivalents ready to go. For example, a computer can add 2 binary numbers as they are already represented by 1s and 0s because of the states of electricity. And it can then just use those states of electricity to make the right calculations when adding, subtracting, or multiplying 2 different bytes. That's just an interesting tidbit of information that if you don't really understand, don't worry too much about it again. So finally, there also exists software that can help us convert bytes from one code to another. So that's another reason why we don't need to become so good at converting decimal to binary to hexadecimal in our heads as well. So in this video, we learned a lot of foundational principles about our computer. We first started off by learning that the byte is a unit of information and storage in our computer. We know that it is made up of 8 bits, or 8 ordered wires that are located somewhere in the computer. And each of these wires either have electricity running through it or not. And when it comes to solving the information problem, the byte is the foundational unit that we need that can be combined to do all the things we want to do with information, to create, store, retrieve, edit, and delete information in the form of bytes at the most granular level. This helped us realize that bytes on their own are pretty much useless and meaningless to us, as they're just wires with electricity running through it or not. We learned that what we also needed to do was create some kind of code to make a byte mean something in real life, where the pattern of that byte, or the pattern of the bits in that byte, equates to something that has some meaning in our lives. We don't forget that a code is just a list of rules that have been written by somebody and agreed upon by many. What this means is that the same byte can mean different things depending on the code that is applied in reading that byte. For example, we saw how we could use the ASCII code to give all the 256 different states of a byte some sort of specific meaning when it comes to the English language as is written, spoken, and understood. And so in this way, we can combine bytes and a code to deal with almost all the information challenges that we face in this world. However, one thing we have not gone through yet is exactly how these bytes exist as wires with electricity in a computer. How is this actually done in practice in a real computer? And so now we've reached a point where we're going to look at the first part of what makes a computer, and that is called random access memory, or RAM for short. Till the next time.